So now that we understand the ideal gas law, we're going to take a look at the ideal gas law in the context of stoichiometry problems. And before you watch me go through this problem, I highly encourage you to try to solve this problem on your own, using what you should remember about stoichiometry and using what we've already covered with respect to the ideal gas law. So pause the video and try this problem on your own before you watch me go through the solution. So the problem says, calculate the percent yield for the reaction shown below if 6.24 liters of carbon dioxide measured at STP is isolated from a reaction of excess urea, 8.93 liters of oxygen measured at 18 degrees Celsius and 1.02 atmospheres, and 12.86 liters of nitrogen monoxide measured at 18 degrees Celsius and 1003 torr. So that as we look at all of the information in the problem, the first number that we have is 6.24 liters of carbon dioxide. When we look at the carbon dioxide in our overall balanced chemical equation, we see that carbon dioxide is a product. That means that the 6.24 liters of carbon dioxide represents our actual yield. The conditions at which this volume of carbon dioxide were measured are at STP. So that's going to be an important piece of information for us, and we'll want to know that piece of information. The next set of information that we've been given in the problem is the fact that urea is present in an excess. That means that we don't care about urea in this particular problem, and the outcome of the reaction depends on the other components. So the next component that we have is oxygen. We have 8.93 liters of oxygen measured at 18 degrees Celsius and 1.02 atmospheres. So that in our reaction, oxygen is one of our starting materials. We know that we have 8.93 liters. This was measured at 18 degrees Celsius and 1.02 atmospheres. So that for this information that has been given to us, we'll be able to plug this volume into the ideal gas law. For this temperature, we will need to convert that to Kelvin, and for this pressure, we can plug that directly into the ideal gas law as well. We are also told in the problem that we have 12.86 grams of nitrogen monoxide measured at 18 degrees Celsius and 1003 torr. So that as I look at this information, here's nitrogen monoxide. I have 12.86 liters. That was measured at 18 degrees Celsius and a pressure of 1003 torr. So that as I look at the information that I've been given about nitrogen monoxide, my volume I can plug right into the ideal gas law. My temperature will need to be converted to Kelvin, and it is the same temperature that I had for oxygen. My pressure of 1003 torr will need to be converted to atmospheres. So there's all of the information that I have been given in the problem. The information that I'm going to be trying to calculate as I go throughout the problem is going to be the relationship between my starting materials and the carbon dioxide. Carbon dioxide is my product of interest in this reaction. As I look at the overall balanced chemical equation, I see that 2 moles of urea plus 4 moles of nitrogen monoxide plus 1 mole of oxygen yields 4 moles of nitrogen gas, 2 moles of carbon dioxide, and 4 moles of water. So that in this problem, the coefficients that are going to be important for me are the 4 in front of my nitrogen monoxide, the implied coefficient of 1 in front of my oxygen, and my coefficient of 2 in front of the carbon dioxide. So for the components I'll be working with, I know that 4 moles of nitrogen monoxide plus 1 mole of oxygen will yield 2 moles of carbon dioxide in this problem. So when we use gases in stoichiometry problems, the major difference that we're going to see is that we're going to need to use the ideal gas law to get to moles in the first step of the problem. So if PV equals nRT, in order to solve the ideal gas law for moles, right there, make sure you know how to manipulate those variables. That is that we have to move RT to the other side of the equation, and that means that N is going to be equal to PV over RT. Make sure you know how to do that algebraic manipulation, because for these problems, if you get that manipulation wrong, you know that all of the work that follows will then also be wrong. So if we start by looking at all of the information that we have for oxygen. In the problem, we were told that we have a pressure for our oxygen of 1.02 atmospheres. We have a volume of 8.93 liters. R is our gas constant, and we were told that our temperature was 18 degrees Celsius, so that when I convert that to Kelvin, I get 291 Kelvin. So that comes from my 18 degrees Celsius plus 273.15, and that gives me that temperature of 291 Kelvin. As I plug all of this into my calculator to solve, make sure you use parentheses for the denominator. And when you solve, you should get 0.381 moles of oxygen gas. Remember that this is the amount of oxygen that you have at the beginning of the reaction. Our second reagent that we're going to be working with is our nitrogen monoxide. And so for this problem, we're told that our pressure was 1003 torr. So if you consult your equation sheet, you'll find the conversion factor between torr and atmospheres. And that is that 1 atmosphere is equal to 760 torr. So that when you do the conversion, you get 1.32 atmospheres, and that's the pressure that we'll plug into the ideal gas law. Again, we're going to be using the equation of N equals PV over RT when we plug in for our pressure of 1.32 atmospheres, our volume of 12.86 liters, R is our gas constant, and our temperature of 18 degrees Celsius we previously converted to Kelvin, so we'll use that 291 Kelvin here as well. When you go to plug in and solve for moles, make sure you use parentheses in that denominator. Make sure you divide by R times T. And when you do that, you should get 0.711 moles of nitrogen monoxide. And again, this is the amount of nitrogen monoxide that we have at the start of the reaction. So now that we have moles of starting material for both of our components, now we're going to do our stoichiometric calculations. If we start with oxygen, remember that these calculations are going to look at what would happen if oxygen was the limiting reagent and all of my oxygen was consumed. We're going to calculate how much product we would make in that case. So in this case, we previously calculated that we had 0.381 moles of oxygen at the start of this reaction. What we see from the balanced chemical equation is that we have 1 mole of oxygen has a relationship to 2 moles of carbon dioxide. So we have a 1 to 2 mole ratio for these components. So that as I set up this conversion, I need to convert from moles of oxygen to moles of carbon dioxide such that my conversion factor is going to be my 2 moles of CO2 divided by my 1 mole of O2. And when I do that calculation, I get 0.762 moles of carbon dioxide that would form if oxygen were my limiting reagent. As we follow the units in the conversion factor, my units of moles of oxygen cancel, and I'm left with units of moles of CO2. And that's what I need in order to understand the stoichiometry of this problem. My next component is the nitrogen monoxide, and we previously calculated that we had 0.711 moles of nitrogen monoxide at the start of this reaction. What we see from the balanced chemical equation is that 4 moles of nitrogen monoxide make 2 moles of carbon dioxide. So that when I set up this conversion, my conversion factor will be those coefficients from the balanced chemical equation, that 4 to 2 mole ratio. So if I take my 0.711 moles of nitrogen monoxide times the fact that 2 moles of carbon dioxide form from 4 moles of nitrogen monoxide, I find that if all of my nitrogen monoxide was converted to carbon dioxide, I would make 0.355 moles of carbon dioxide. As I check my units, my moles of nitrogen monoxide cancel. I'm left with units of moles of CO2, and that's exactly what I'm trying to solve for in this problem. So remember that at this point in my stoichiometry problem, I know 3 things. I know my limiting reagent, I know my reagent in excess, and I also know my theoretical yield. So that as I compare the values that I just calculated, this 0.762 moles of carbon dioxide here tells me that if all of my oxygen is consumed, this is the maximum amount of carbon dioxide I can make. I can make anything less than that, but nothing more. For nitrogen monoxide, if all of my nitrogen monoxide is consumed and converted to product, this is the amount of carbon dioxide that I can make. I can make anything less than that, but nothing more. So if you remember back to our discussions on limiting reagents, what we're going to do is we're going to compare these amounts of product. We're looking for the lesser of the two for the amounts of product, because that means that we will have enough of both of our reagents to make that amount of product. So I can make 0.762 moles of carbon dioxide or 0.355 moles of carbon dioxide. And those calculations tell me that I have enough of both of my reagents in order to make this 0.355 moles of carbon dioxide. So that this value here becomes my theoretical yield. That tells me that my nitrogen monoxide is my limiting reagent, and my oxygen is my reagent that's present in an excess. So that at this point in the problem, I'm going to be working to calculate my overall percent yield. We know from the beginning of the problem that we had 6.24 liters of carbon dioxide that was isolated, and that volume was measured at STP. This is our actual yield. So right now I know my theoretical yield is 0.355 moles, and I know that my actual yield is 6.24 liters. So in order to solve this problem and calculate my percent yield, I need to make sure that I have the same units for my theoretical yield and my actual yield. I also need to make sure that I know the measurements for my theoretical yield and my actual yield under identical conditions. That is that because my actual yield was measured at STP, I need to convert this theoretical yield of 0.355 moles to a volume at STP for my gas. And so that's what I'm going to do down here. When I solve the ideal gas law for volume, I find that V is equal to nRT over P, and as I substitute in for the values that I know, I have my 0.355 moles, which was my theoretical yield. R is my gas constant, 0.082057. My temperature at STP is 0.00 degrees Celsius, which is equal to 273.15 Kelvin. So this comes from my STP. And at STP, I also know my pressure is 1 atmosphere. So that as I plug all of this in and solve, I find that I get a theoretical yield of 7.96 liters. So this represents my theoretical yield, of which up here I calculated the moles. This is my theoretical yield in units of liters when measured at STP. So now I know my actual yield and my theoretical yield under the same conditions. So now I can calculate my percent yield. That's going to be my actual yield divided by my theoretical yield times 100. So my actual yield of 6.24 came from the information that was given to me in the very beginning of the problem. This theoretical yield of 7.96 liters was what I calculated over here. And when I do that calculation and I multiply by 100, I get 78.4% as my final answer. As an alternative, you also could have converted this actual yield of 6.24 liters to moles using your STP conditions. And in that case, you should have gotten approximately the same answer as we got here. Either strategy is fine. So I do want to show you an alternate strategy that you could use to solve this problem. And that is taking advantage of what we know about the molar volume of an ideal gas. So what we know is that 1 mole of any gas at STP has a volume of 22.4 liters. That's at STP. And so because in this problem the carbon dioxide as our final product was measured at STP, that allows us to simplify our calculations a little bit. That is, that we can use that molar volume of a gas as a conversion factor. We can take our 0.355 moles, this was the theoretical yield that we calculated. We can take that theoretical yield and we can use our 22.4 liters over 1 mole as a conversion factor to get directly to liters. We did the same calculation by plugging into the ideal gas law, but this works too, and it can be a little bit of a shortcut if you understand when and why we can use this. Again, this only works because our gas is at STP. If our gas was not at STP, we could not use this simplification. So that means that we can use this as a conversion factor. When we use the calculation this way, we get 7.95 liters of carbon dioxide. That's a little different from the 7.96 liters that we calculated previously, but that just has to do with the difference in the significant figures throughout, and those minor differences will be okay in the end. If we use that information to calculate our percent yield, we're going to take our actual yield divided by our theoretical yield times 100, and when we do that, we get a final percent yield of 78.5% in this problem. So that anytime we have a gas at STP, we can use this 22.4 liters per 1 mole as a conversion factor to help simplify some of our calculations.